Hey everyone. All right, so welcome back to grade 12 University Physics here with Mr. Stone. So this is Unit 5, Lesson 6, and we're going to start talking about something a bit weird. We're going to talk about the wave-particle duality. Okay, so this is where things start to get strange. Okay, the weird and wonderful world of quantum mechanics starts to take over. Okay, so before we move on, okay, just a quick warning. All right, so we are starting to talk about quantum mechanics. Right? Now, we're going to encounter some phenomena that are nothing like what we directly experience on a macro scale. Okay, this is everything at angstrom scales, below 10 to the negative 10 meters, and at very, very small masses, things like electrons. We're going to be talking about things like waves and particles and springs and things like that as analogies, basically, because nothing really behaves like that at the quantum level. We have mathematical models that can predict things exactly for, let's say, things like um, electrons and photons, things like that. But and we can talk about them in terms of like we can talk about atoms as being on springs. We can talk about clouds of electrons. Really, it's basically just mathematical models. Okay, and we have to use mathematical models, and we have to use our imagination to treat them as things like particles and things like that, and clouds and springs and that. But really, nothing in quantum mechanics is like what we experience in the large scale world. Yeah, and this is a scary concept, but if you think you completely understand quantum mechanics, it means you haven't thought about it enough, right? There are moments where you're like, oh, that makes total sense, but really, it doesn't. There's a lot of places where things sort of cause us to get really confused, and a lot of times where we confuse ourselves in this. Okay, so just be very careful and remember that in the end, we have mathematical models and that's it. It's okay though, because nobody truly understands quantum mechanics. It's just you can't understand quantum mechanics. Right? You can know how it works and we can understand the theories, but truly to understand it in the same ways we can understand how momentum is conserved and things like that. Macro scale physical phenomena, we can understand that because we can see it, right? These things are at a very small scale and things get very strange. Okay, so just let's get that out of the way. Just a little preface of all this quantum mechanical weirdness because things are going to get weird. So let's do an example to help us understand some of this weirdness. Okay, so let's imagine a gun. It's a very poor gun. It randomly fires bullets in this sort of random spread. Okay. Now we're going to fire this gun. It's not actually a gun, but it's just imagine these particles are being fired. These discrete particles. That's the important part. We're using the idea of a gun because they fire bullets one at a time. It's these discrete things that are going to be emitted, kind of like you can use an electron gun, basically. Like think about it as some sort of particle. Okay, and it's being fired at this double slit, just like the double slit problem in Young with light. And we're going to put a wall behind it, and we're going to catch the bullets. We're going to see what happens to those bullets. And the question becomes, what's the probability that a bullet will pass through the hole and arrive at a backstop at distance x from the center? So what are the probability? What's the shape of the curve of the probability of bullets that go through these holes? And we're going to have some sort of detector to catch the bullets. And we'll see that there's going to be a sort of a probability from the first one, right? It'll go through here. And the probability distribution will look something like this. And a large hump about here, which is directly through there. But then there might be some strays. It might bounce off the sides, right? It can get to here because it bounces off of here. And it'll be some sort of probability distribution. It's most likely to be somewhere at this x position, but then the probability drops off as we go. For 2, we can have a probability as well here. And then the overall probability is going to look like this hump here. It's most likely going to be in the middle because that's the combination of the two probabilities. So the probabilities, the sum probability here, this P12, for all the particles that travel through both gaps is going to be given by this. And it's quite easily calculated as the sum of the probabilities because they are discrete, right? Because they're objects. And as they go through one or the other, we can come up with these two probability curves and then just add them together, right? And if these were farther apart, then these humps would be farther apart, and then it would look like there'd be two humps instead of one. And it doesn't matter though. It's simply the important part of this is this equation at the bottom here, that the probability is just the sum of the two. What we're looking at is the probability of the arrival of the individual lumps, the individual bullets, the discrete objects. And there's no interference because one bullet's being fired at a time. There's no way that two bullets are flying in the air and can sort of bounce off of each other. So the probabilities just become a simple discrete problem, right? The bullets can go either through one hole or the other, but they can never go through both holes, right? The problem with light, the reason that light interfered with itself was that it was there was a light wave going through both holes, and as it reached the detector on the backside, the screen or whatever it was, there was some sort of path length difference between them, and there'd be some sort of interference. But they're arriving at the same time. The flight time is the same, right? So they meet at the same time. There's no way that bullets in this example here. There's no way that a bullet can travel through. A bullet somehow, same bullet goes through both holes and then comes back and then causes interference. That's impossible, right? So if we use waves, on the other hand, that is possible. What's the screen going to show now if I have waves? If I have some sort of wave source, light, something that produces these waves. In this case, there is no discreteness. There's no lumpiness in the wave. A wave can simultaneously go through both holes and then interfere due to phase differences, just like in Unit 4 with light, and we'll end up with this interference pattern. And the intensity, this is a bit beyond us, but we ended up, we've seen this pattern here, right? Because of the path length difference between the two, right? That this path length difference here caused an interference. Okay, but important, don't worry too much about the form of this equation here, but it's just saying that it's not a simple sum, right? This is going to be equal to right, h1 squared plus 2h1 h2 plus h2 squared, right? So there's this cross term that causes all the problems. It causes the interference, basically. Don't worry too much about the mathematical form there. That's a little bit beyond us. But just go think about Unit 4 where we talked about how waves interfere, right? And this path length is going to cause interference. And this happens because a wave is able to travel through both holes at the same time, right? A wave can simultaneously go through both holes and interfere. That's what happens in Unit 4. Now what we're going to try is do the exact same experiment with electrons. Electrons are very, very small. You can do this. We can make an electron gun, and it's going to randomly fire off electrons at a random angular spread by just heating up a piece of metal. Okay? And the interesting phenomenon was that if we have a high enough voltage, so we're firing off electrons at high enough speeds, and if the gaps are small enough, if this spacing here is small enough, let's say using the atoms of a crystal, so using the nuclei of a crystal, the crystal lattice, the crystal structure of something. A crystal just means that there's atoms in a sort of organized fashion. There's a crystal structure, meaning it's a cube or hexagon or something like that. Some sort of organization, geometrical organization of atoms in this, what we call a crystal. That's the definition of a crystal. So if we use those gaps between atoms inside a crystal as our holes, because we need the space. Remember, the only time that we would see interference with light was when the size of, or the spacing between them was, in the order of the light. Right? We needed micron spacing for us to see nano 100 nanometer light, right? So we need very, very small gaps. So when electrons are very, very small, we need really, really small holes. So we use a crystal. The weird thing that happened is we got a interference pattern. This is a picture of an interference pattern of electrons as they traveled through a crystal. This was first shown by two physicists, Davidson and Germer. This is a very famous photo of the interference pattern caused by electrons traveling through a crystal lattice. So what does that mean? Electrons are interfering with each other? So somehow we have to come up with, a way to show that. And really what it says is that electrons, which are matter, electrons are not light. Electrons have mass. Right? And we've shown that they're different, right? If it's something that doesn't have mass, it can travel the speed of light, but electron has mass. It's a thing. It's a particle. Right? We can just say that this is an electron. However, it has to have now, because of this experimental proof, it has to have some inherent wave nature. There has to be some wave-like properties to an electron to allow it to interfere. And using this idea of Young's double slit, an electron has to be able to, the same electron has to simultaneously go through both gaps. And that means that they're not discrete objects, which is mind-boggling. So this is saying somehow this electron, because we have this screen and it's showing an interference pattern, that electron that got fired from that gun somehow managed to go through both holes at the same time, and then using some sort of wave-like property interfered and produced an interference pattern. Now, even stranger. Okay, just wait. Look at that probably has to sink in a little bit. Electrons have wave-like properties and can simultaneously go through two holes at the same time. What? Okay, but this is a bit stranger now. If I change the apparatus, and instead of having a detector on the screen, like using the screen to detect it, instead I somehow put a detector at the holes, then I no longer see a diffraction pattern. There's no longer, well, I can't see the diffraction pattern because there's no screen, but now I'm seeing electrons individually hitting one or the other. Okay, now I see a probability distribution like the gun in the first example. The diffraction pattern disappears. If I'm looking at the holes, the diffraction pattern disappears. If I look at the screen, I see an interference pattern. What? How is that possible? How are both of those things possible? And this leads us to the important big idea of quantum mechanics. The act of observing. Okay, when we look at something, when we observe something, it is no longer an objective thing. We can no longer observe something without also being inside the system. How we look at it changes how it behaves. If I look at the screen, I see diffraction. If I look at the holes, there's no diffraction. If I look at the screen, electrons are acting like waves. If I look at the holes, the electrons are acting like particles. So this leads us to the big idea of quantum mechanics. When we observe something, we disturb it To observe is to disturb. The act of observing on small scales has an effect that disturbs the system, the situation here. No observation can be done such that there's no effect on the system. Okay, typically, when we look at things, when we do stuff here, we talk about large macro scale objects. Us looking at them or doing things, observing doesn't really make a difference. Okay, but we got to think about small scales here. The smaller scale something is, the harder it is to see because we need to use smaller and smaller wavelengths. Right? Think about it in like a statue. Okay, you're blind. You can't see a statue. Let's say there's this, the statue of David. Okay, let's say you're blind, but you can't see it. The only way that you can observe it is by throwing, say, tennis balls at it. And you're going to throw tennis balls very carefully, and you're going to measure where the tennis ball bounces, how it bounces off of it. Okay, that tennis ball is going to hit David. It's going to bounce off. Now, the tennis balls are, a good size. They're like, 8 centimeters or something like that. So you'll be able to get an idea of David's general shape, where his arms are, where his head is, that sort of stuff. But you won't be able to see details. You won't be able to see his face. For that to be possible, you're going to have to take those things that you're throwing at it, those balls, and get them smaller and smaller, so that they can bounce off of the fine details. Right? You're going to start using marbles, and that'll give you a better idea of let's say the face, where his eyes are, nose are, and stuff like that. So still not going to get it. You're still going to have a blurry picture. So to get more discrete observations, more fine tuning of your picture, your picture being created by throwing things and bouncing off of it, you're going to have to get them smaller and smaller and smaller. In the same way, for us to observe very small things, we have to get wavelengths that are smaller and smaller. For example, for us to see atoms, we have to use wavelengths of the order of nanometers. And we learned, or we're going to learn, we learned last lesson that the energy is proportional to the frequency. So the higher the frequency, the lower the wavelength, the higher the frequency, the more energy it has. Okay, so then that energy that we're giving to it as it collides with it disturbs it, changes it. So it's no longer where it was. Let's say we have an atom and we want to observe it. It's very, very small. Let's say an electron. We want to observe an electron. We're going to have to fire something that's very, very small at this. But that it's going to be like an X-ray. And X-rays are high energy photons. It's going to hit that electron. If it does hit that electron, it's going to give it a huge amount of energy. And it's going to bounce off somewhere. And it's no longer going to be where it was. So observing things at these small scales necessarily disturbs them and changes where they were. So we cannot, and so when we observe things, it changes how the situation acts. This active observation becomes, critical to how things behave, how we're looking at things. If I look at something to be a wave, it'll act like a wave. If I want something to be a particle, it can be a particle. It can be both. There's the big idea, okay? Particles and waves. Things can act like particles and waves at the same time. That's what I'm trying to get here. So what is light? What is matter? Is it a wave or a particle? And the answer is it's both. Its behavior depends on the way that we observe it. And we call this the wave-particle duality of quantum mechanics. Okay? And how can we picture a particle that's a wave and a thing that's a wave and a particle at the same time? We don't. Okay, it's impossible to visualize. This is what I meant by these things do not behave like what we observe in our normal everyday life. Okay, it's impossible to actually visualize these things. We have to use the mathematics of quantum mechanics to assign probabilities to these things. Okay, quantum mechanics becomes an exercise in probability. Okay, and Unfortunately, I'm not going to go into all the math. The math is way beyond high school, but we're going to talk about these things from a sort of heuristic point of view. So let's back up a second, okay? So we just said, because of Davidson and Germer's experiment here, we said that an electron is a wave. So waves have wavelength, right? They have frequency. So how is that possible? So using the Compton's momentum relationship that we developed last lesson, right? That the momentum of light is Planck's constant divided by the wavelength of that light, right? The momentum of a photon is inversely proportional to its wavelength, or another way you can think of it is it's proportional to its frequency. The more frequency, the more momentum. Now that's using a massless photon. But now let's say we have a non-zero mass particle. We can use our classical description of momentum, which was that momentum is mass times velocity. And if we replace that in our expression here for p, we can solve for lambda and say that the wavelength of something is equal to Planck's constant divided by its mass times its velocity. And this is the de Broglie wavelength, named after the famous French physicist. And it defines a wavelength of matter, which is a very strange idea. Now remember, Planck's constant is very small. So if we try to do this for a normal object, let's say we have a 100-gram ball and it's traveling at 20 meters a second. Okay, I throw a baseball. What's the wavelength of that baseball? Plugging in our numbers into this formula, right, using Planck's constant is 6.63 times 10 to the negative 34, so incredibly small number. Joule seconds divided by kilogram meter second. We end up with a number of a wavelength here in the order of 10 to the negative 3 meters. Incredibly small wavelength. Really, it doesn't matter. So when we talk about macro scale things, big things, the wavelength is so small, the wave-like behavior is negligible. It doesn't really behave like a wave because we're dealing with these large things. Because these m's, these masses, are so much bigger than Planck's constant. Okay. Just quickly, do the units work here? Right. Joules is kilogram. What's that? Kilogram meter squared per second squared. So I'll cancel the meters. Second squared, I'll cancel that's one of the seconds. That per second will cancel the other per second. And the kilograms will cancel, and we're left with just the 1 meter. Yeah, the units all work out here. Now, so again, the big idea here is that big objects, regular macro scale objects, the wave-like behavior is negligible. But let's now think about instead an electron that has a kinetic energy of 24 electron volts. That's a very, very small thing. What happens in this case? So let's just go back. Remember that now 24 electron volts is small. That is not a relativistic kinetic energy, so we don't have to worry about relativity. Kinetic energy in this case is just going to be our typical classical kinetic energy, half mv squared. Now, if I multiply by 2m on both sides, I'm multiplying by 2m on both sides of here, right? I'm going to get the 2's will cancel, and I get m squared. V squared is equal to 2mk. And I can take the square root of both sides. Sorry, I can square, like, basically, the idea here is I get mv squared, right? This is m squared. V squared is the same as mv squared. mv squared is just p squared. That mv, right, the mass times velocity is just the momentum. So the momentum squared is equal to 2mk. Then momentum is just the square root of 2 times the mass times the kinetic energy. This is just playing around with the two equations of kinetic energy and momentum. So we can get an equation of momentum that involves kinetic energy. So now we use our our Compton equation, that lambda is equal to h over p, the momentum, substituting in my new formula for p, and then substituting in my values. Now notice, Okay, so this was 10 to the negative 34, and this is 10 to the negative 31. Okay, so these are similar, but and also this was in electron volts, so I have to use the conversion here from joules to from electron volts to joules, right? The elementary charge, and I end up with a wavelength in the angstrom region. So electrons have a wavelength, have a de Broglie wavelength of the order of 10 to the negative 10, which is the same as the size of the crystal lattice. That's the size, that's in the order of those crystals that Davidson and Germer fired those electrons at and got diffraction. They got diffraction because these electrons at these speeds here, have an inherent wave-like behavior. They have an inherent wavelength that is in the same order same size as the spaces between the atoms of the crystal. So we ended up with diffraction happening. Okay, so when we talk about big macro scale objects, the wavelength doesn't really matter. But small things, very light things like electrons, definitely have wave-like behavior. Okay, so an electron, which we've always treated as this, this negative charge particle, is a particle, but it's also a wave. It's both. It can behave like a wave and a particle. It has particle-like properties, and it has wave-like properties. The objects we experience have wave-like properties, but they're completely negligible to our everyday understanding. Okay. So, in summary here, this has been we're 27 minutes, so it's a pretty long lesson. I apologize. So it's a big lesson, some big ideas that hurt the brain. So to put it all together, okay. In summary, both light and matter are governed by the same quantum mechanical framework. There's a quantum mechanical mechanism that governs all of these things, light and matter together. Things can have wave-like properties and particle-like properties, and whichever one we want to observe is the one we're going to get. And the act of observing something must necessarily disturb it. To observe is to disturb. Photons, light, wave light, these wave-like disturbances in the electromagnetic field have particle-like properties. They have particle-like momentum, which is defined by h over lambda. And electrons have wave-like, electrons, these things, matter, that has, that are particles, stuff, has wave-like wavelength, which is defined by the de Broglie wavelength, h over mv. Okay, so some big ideas, some scary ideas. Again, if you don't understand this stuff, it's okay. Nobody does. Okay, we're just we're slowly trying to build an idea, and next, these ideas are going to lead to some even stranger things, which is the next one, which is called uncertainty, which we're going to have to talk about next. And things get even weirder. Just be careful. Any questions, just send me a message. All right? So that's it for now. Just a couple questions. Simple questions using the de Broglie wavelength formula. It basically is calculating de Broglie wavelengths. Okay? Calculating the wavelength of matter. That's awesome. All right. Okay. So started quantum mechanics. Our brains are probably hurting. Okay. Well, I'll be talking to you later, and best of luck.